Okay, so thank you. I'm very happy to present this work here on Profinite, lambda-terms, and parametricity. So I'm a PhD student since September 21 with Paul-André Méliès and Sam van Rol, and I'm going to present joint work with my two advisors. So for the context, the regular languages of finite words have been extensively studied in theoretical computer science. And in particular, there have been a lot of different tools that have been developed to study languages of words. And in particular, there have been topological tools coming from stone duality and other ideas like that, and profiniteness. And so at the same time, there is another notion of regular languages, but this time for lambda terms, which was introduced by Salvati, and using semantic tools in interpretation. So what I'm going to present here is a first step in lifting these tools, profinite tools, from the case of finite words into the case of languages of lambda terms. And in particular, I'm going to present a notion of profinite lambda terms, which we show generalizes the notion of profinite words, which is at the heart of the profinite methods for automata theory. So just to begin with, so I'm happy that Tito have already talked about what I'm going to present. It's going to be easier. So if we have a finite alphabet sigma, then for every finite monoid and every interpretation function p interpreting each letter into the finite monoid, if we have a subset f of the finite monoid, then we can define the language of words which are sent in the finite monoid M to an element of S. So you can think of S, F as the final states that we ask for to have regular languages of words. And so if for a finite monoid M, we can look at all the languages that are recognized by M by looking at all the subsets of M, and this gives us this Boolean algebra reg M. And we define we show that it's equivalent to have monoids, finite monoids like that, or deterministic finite automata. And so language L is regular if and only if there exists a finite monoid M such that it is recognized by M. Okay, so this is for finite words. But so I've talked about lambda terms, but I'm going to first show how we can encode the words finite words into the simplified lambda calculus. So it is well known that we have the Church natural numbers. So if I have a natural number n, then I can encode n into the simplified lambda calculus in this way. So basically, the number n is represented as a function which iterates n time its argument. So it applies n time the function here written s. But this is just for the one-letter alphabet, which is n, okay? But if we have any finite alphabet sigma, we can do the same encoding. So for instance, here, if I have the word ABBA, it will be interpreted, encoded as this open term in this context. And by closing it, we get this simplified lambda term. So it takes basically a function associated to the letter A, and then the letter B, and it takes an input state, and its output is a result of running the word. And in this way, we have the type Church sigma for every finite alphabet sigma. Okay? So now about the interpretation. So if we have a Cartesian closed category, we can interpret the lambda calculus inside C. So if we have an object Q, we can build this object, the interpretation of A at Q, in this way by induction on the simple type. And this gives us, we can build an interpretation function, which is this semantic bracket, which goes from the simply typed lambda terms of type A, modulo beta and eta, to the points in the categorical way of this object, the interpretation of A at Q. So in our particular case, we will be interested in fin set, which is a category of finite sets and functions between them. And in that setting, if I take a word, a finite word, I first encode it as a simply typed lambda term, and then I can interpret it into the model at a finite set Q, and it will give me a function which is an element of this set. So, and it will describe how the world will interact with automaton. Okay, and now you see that we have almost the same slide as before, but in this Cartesian closed setting. So if I have a finite set Q, then I can consider for any subset F or AQ all the lambda terms which are interpreted as points of F. Okay, so this gives me a language. Now, for any finite set Q, I can have this Boolean algebra reg Q, which is all the languages which can be recognized by Q. So Q, in a way, is like the pixel resolution that you look at, and the bigger Q is, the more you will have, you will be able to have some information, precise information. And we define reg in this way by saying, okay, so a language is regular if it's recognized for some Q finite set. For the moment, it's not a Boolean algebra. So now, just like some kind of sanity check, if we take the regular languages of lambda terms of type Church sigma, then this is exactly the usual regular languages of finite words. So what we're presenting here, which in fact is the work of Salvati, but rephrased a bit differently, is a work which extends the theory of regular languages of finite words. So we can show that if I have one language, I can read the other, and vice versa. Okay. And so about this set reg A, so a key observation that we will use in all the talk is that logical relations play very well with all these language stuff. And so if I have a relation R between two finite sets Q and Q prime, then I can build the logical relation associated to it, which I write in that way, which is defined using the Cartesian closed structure. And in particular, the key property is that if the base relation is a partial surjection, then the lifted, in a way, relation to the type A will also still be a partial surjection. And this is very useful in proofs. So in particular, if I have a finite set Q, which is of greater cardinality than Q prime, then the set reg Q contains more languages than Q prime. So it really shows this idea that we have a notion of precision. And so in this way, we have a diagram which is directed, and we can show that the set reg A is a colimit of this diagram, which justifies the fact that it's a Boolean algebra. Okay, so now about the profinite world. So I like to have this image. So imagine first, like for 1 minute, that we have this object. And we want to light it up in different ways. We have different sources of light. And for each light that we put, we have a shadow. So the light is the question that I ask to the object, and the shadow is like the answer that I get. And of course, if I have some tangible object like that, if, for example, I have a very sharp light, then the shadow will be very, very sharp and not blurry at all. And if I move smoothly the light around the object, the shadow will move also smoothly. So in fact, what I'm trying to say is that if I have a real object like that, the system of shadows that I will get will be coherent. I cannot have inconsistencies between the shadows because they all come from this physical object. And so now what I'm going to say is, okay, actually, what we are interested in is only the shadows, not really the object itself, and we are going to study it only with that. So let's remove the object, and we just study the results to the question that we may ask to it. So a profinite world is really something like that. It's like a family for, so we range in all finite monoids, and we range in all functions going from sigma, set theoretic functions, to this finite monoid M. And for each function like that, which is like, if I interpret my letters in this way in this finite monoid, what result will I get? And so the naturality condition is saying that we have coherent results, coherent answers to the questions. And so now, if I have a finite word, W, then of course I get a profinite word by interpreting the word into the finite monoid. So now just an example of a profinite word which is not finite. We are going for that to use the fact that we interpret in finite monoids. And this is very important because this restriction will make new phenomena appear that may not be in general definable if we take all monoids. So if I have a finite monoid, for every element, I have an idempotent power of this element. And this is not, of course, true in, let's say, the natural number, which is an infinite monoid. And so now if I have any letter A in sigma, I can define a profinite word, which is some kind of infinite iteration of A. And in all the finite monoid M, with this interpretation of the letters, then the answer that I will get, where am I in the monoid with this P, is at the maximal iteration of P of A. This is what this equation means. So, okay, for every profinite word, actually, I can build this profinite word u to the omega, which is some kind of infinite iteration of this profinite word. Okay, so now, what is the link between these profinite words and the regular languages? Because for the moment, it's not clear. So there is this dual equivalence of category between stone spaces and Boolean algebras. So it says that if I have a stone space, I can build a Boolean algebra from it, which are its clopens. And if I have Boolean algebra, then I can build a stone space, which is its space of ultrafilters. And this contravariant, okay? And now, what is interesting is that we have this relation between reg sigma, so that we have defined using finite monoids, and the monoid of profinite words. So this profinite monoid, in a way, is like the mirror image of the Boolean algebra of regular languages through this stone duality. So actually, it's very natural. So now we want to do this, but for lambda terms. So the first step is the following. So we say that for any finite Q, we had this set of all the higher order states in which we may arrive by interpreting lambda terms. But what is actually interesting is this set here of definable elements, because if we have states that we never touch with any lambda term, it won't be useful for regular languages. So this set is what is actually interesting. And now this set turns out to be the stone dual of this Boolean algebra. By the way, so this set is finite, and this Boolean algebra is finite too. So the topology on the left is just a discrete topology. There is no interesting topology for the moment. And now we can define the profinite lambda terms. Because we had a diagram of finite Boolean algebra, from which we had its colimit, the reg A. Now we dualize the same diagram, we get this diagram, and it is co-directed, and we say that the set of profinite lambda terms of type A is the limit of this. And see here that the question is like a finite set, and the answer is I am in that higher order state. So it lives in a perfect harmony with stone duality, as the Boolean algebra of recognizable languages a la Salvati is the Boolean dual of profinite lambda terms of type A. So more concretely, a profinite lambda term of type A is a family of elements for each finite set Q, and which is natural in this way, because of course it's a categorical limit. Okay, so now all the profinite lambda terms assembled into a Cartesian closed category, which we call prolam. And this means that we can program with a profinite lambda term. It's some kind of profinite lambda calculus. Because it's a Cartesian closed category, we have a functor from lam to prolam. So lam is the usual simply typed lambda terms, and which is given by this formula. So if I have a lambda term m, then the profinite lambda term that I will get from it is just all the interpretations for all the Q. And this, we may ask whether it's injective or not, and we want it to be injective, and it is because of Stassman's finite completeness theorem. Okay, so now an interesting fact is that we had this bijection that is well known in the lambda calculus community, and which actually lifts to the profinite settings. So we had that lambda terms of type church sigma are words, basically. And here, profinite lambda terms of type church sigma are exactly the same thing as profinite words. But this is only the first step, because I've shown you a profinite word, which is not a finite word, which was built from iterating like an infinite number of times, even though it's a bit more complicated. And now we can show that we have exactly the same operation, but built inside the profinite lambda calculus. So we have this term. I don't want to explain everything, but we have this term, which is of type church sigma arrow church sigma, and which is exactly like an implementation of this operator that we had on a profinite word. Okay, one major point is that our notion of profinite lambda terms interacts very nicely with Reynolds parametricity. So if we have a family of elements theta q in this interpretation set, we say that it's parametric if for all relations R, the two elements at Q and Q prime are related via this relation at type R. So now notice that for the two differences with the definition of profinite lambda terms are that the elements theta Q are not asked to be definable. It may not be the interpretation of any simply type lambda term, but the family, we ask it to be parametric with respect to all the relations R, and not only the partial surjections that we have used so far. Now, so we have two theorems. The first one is that every profinite lambda term is a parametric family. So actually, being parametric with respect to partial surjection is enough to be parametric with all relations when we are definable at every Q. And the second theorem is converse at church types, is that if we have a parametric family of type church sigma, then actually this comes from a profinite lambda term. And what I want to stress here is that this in some way is a parametric theorem, because we say that if we have a family, which is basically a semantic element, if we have a semantic element which verifies some good property, i.e. parametricity, then it must be the interpretation of a profinite lambda term. And so the proof uses some term that we call lambda-terms, which are basically terms enfolding the types in themselves. And we use it to show that the parametric families are definable at every Q. So that's it. So what I want to do as future work is to generalize the notion of lambda-terms for every higher order type, and not only church types, and to see, I mean, perhaps we will have also a counterexample, we don't know yet, and also to investigate a notion of MSO logic for these lambda terms, and to see if we can have some kind of logic for lambda terms. So that's it. Thank you.
I have a question. Well, that's rather misunderstanding. But when you talk about how one thing is stone tool of another, what categories are they really in?
Ah, okay.
Because like you had this external statement, but then you went inside. Yeah.
So we have the category of stone spaces, which are compact and totally separated spaces. And we have the category of Boolean algebras. And so we have, so here it's two functors. If I have a stone space, then I can consider the Boolean algebra of all Klopen sets. So it's union, stable by union, intersection, complement. And if I have a Boolean algebra, then I consider the space of ultrafilters. So ultrafilter is a way to like select coherently in the Boolean algebra an element. So if it's a finite Boolean algebra, it's just going to be the atoms of the Boolean algebra because it's finite. And if it's infinite, it's going to be more complicated. So is it...
I mean, like, but then when you say that you're monoid of profinite words, like, where does this object live?
Ah, okay, I see. So, okay, this statement should come with a forgetful functor. Because Okay, it's a monoid, but here I only talk about the underlying topological space. I don't consider, but there has been some work by Gerke, Grigoriev, and Pin showing that actually we can extend this stone duality to like stone monoids on the left and Boolean algebra with residuation on the right. And in that setting, this Boolean algebra also has this operation which justifies this duality.
So you have like basically, well, forget plug pointers now, like this commutative diagrams and duals.
I mean, either you consider it in that case, in which case here you have the forgetful functor, or you consider it in the more precise case. Yeah.
Your extended calculus, the Profinite calculus, do you have some kind of fixed point or something like this?
So we have, if I go to this slide, so we have this lambda term, which is actually, this is only the profinite integer 1 to the omega. Okay, but we can use it to produce these profinite lambda terms. So in that setting, we don't have a fixed point operator because actually the set of profinite lambda terms of any type A is non-empty if and only if the lambda terms, the set of lambda terms is non-empty. And there is no lambda term of type ORO, RO, so there must be no profinite lambda terms of this type. But there are other settings that we are investigating also, in which we have some fixed points. And actually what is interesting is that we have some greatest and lowest fixed points. So which combine very well with these ideas of iteration coming from the profinite world.
Yeah, maybe to just clarify that when you say setting, you mean category. I mean,
yeah, sorry.
For a category theory audience, basically the definition is parametric in a choice of category C.
Yeah.
And here, what Vincent has presented is being set, essentially. Right?
So simply that lambda calculus can be modeled in Cartesian closed categories. So how about the models of this kind of profinite lambda calculus? Or can you?
I don't know. The problem here is that we don't have a syntax. It's a very semantic definition, and so and for the moment, I mean, we are nowhere near to find a syntax for this profinite lambda calculus. So given that, I'm not sure we can formulate easily a notion, but it's an interesting point. Yeah.
More questions? Okay, let's time to pick your game.